All right, let us now look into the main players in algebraic geometry, namely zeros of polynomials. So first of all, we want our polynomials to have zeros, and that's why from now on we will be working over algebraically closed fields. Let's first define what a affine space is, where all our zeros eventually will happen. So a affine n space over K is simply, so K is our algebraically closed field. This is simply the set of n tuples of elements in K. Now, why do we use such fancy notation? Why do we not just write K to the power n? There are a few reasons. One reason is that we want to consider this as a set. And when you see K to the power n, you might think of this as a vector space or a product of something, but we don't want to think of any algebraic structure of this. This is just so far a set. And of course, this can be defined for any field K. It doesn't have to be algebraically closed. And many of our definitions and some of our results will work for non-closed fields. But for now on, and for some time into the course, we will only consider algebraically closed fields. The other reason why we do this is that we want to do this more generally in the future. So we want to write something like A and K over R, where R is a ring over K, or a ring containing K. So we want to view this thing as a functor from the category of rings to some reasonable category. This is what we will do when we look at schemes. But I'm getting ahead of myself. Let's get back to our current situation where we work over algebraically closed field. And when you work over an algebraically closed field, the field itself somehow contains enough information that you don't have that much motivation to look into rings containing that field because of their algebraic closure. So affine n space, this is just n tuples of elements of K. And so each polynomial in the polynomial ring in n variables, same n, will define a map from affine n space to K simply by application or by evaluation. So wherever you would have put your variables in the polynomial, you put the coordinates of this point. And now we can define our main objects, namely zero loci of rings. Loci is the plural of locus. So given a set of polynomials in several variables, the vanishing set V of f, or the zero locus of f, where f is this set of polynomials, that's simply the set of points in affine n space where the polynomial vanishes. So this means that f of x1 to xn equals 0. We will always abbreviate x1 to xn by x. And an algebraic set is a set of this form. So an algebraic set is a subset of the affine space that is the vanishing set of some set of polynomials. So far, the set of polynomials is quite arbitrary. It can be finite, can be infinite. Now, I'm calling this algebraic set, and this is somehow a way to sneak in the definition of affine varieties. For some, in some texts, in some pieces of literature, this is called already an affine variety. But in some other texts, so affine varieties will somehow be the simplest kinds of algebraic geometric objects we will look at. They will be the equivalents of surfaces and curves and things like that. And so in some texts, you require more regularity. So you require something more. You do not take the vanishing set of just about any crazy collection of polynomials. And in also, what is to me more, how to say this, important from a philosophical point of view, but not strictly speaking mathematically, is that in again some text, you want, so if your algebraic set is called X, you don't want to consider X as an affine variety, you consider X together with some ring of functions on X. And this pair is your affine variety. Now for the case of affine varieties, the ring of functions on X is somehow determined by X. So it doesn't add information, but in the general philosophy of varieties, algebraic varieties and more general things than that, you will need the ring of functions. So for now, let's just call these algebraic sets, knowing that they are the building block of everything that we will do in algebraic geometry in the future. So let's look at some examples. The empty set is an algebraic set because the empty set is the vanishing set of the constant polynomial 1. And the whole affine space is the vanishing set of the polynomial that's constantly 0. So these are algebraic sets. Any point, sloppily, I mean, of course, the set containing any one point is an algebraic set, because if the point it has coordinates x1 to xn, then the set of x, this is the vanishing ideal of t1 minus x1 to tn minus xn. These polynomials, the set of x on which all of these polynomials vanish is just this point, x. As a corollary of a proposition we will see in the next slide, any finite set of points is an algebraic set. And linear subspaces are algebraic sets, because from linear algebra you know that such subspaces are zeros, are given as the zero set of some set of linear equations, and linear equations are of course polynomials. You can generalize this a bit more. A linear subspace is required to go through the origin, but here you can take more general shifted linear spaces, affine spaces if you wish. So let's look at some properties of these algebraic sets. If we take two families of polynomials in n variables, and suppose that one family sits inside the other, then their vanishing sets sit inside each other, but in the opposite order. Why is this? This is because V of f, this is the set of all x in the affine space, such that f of x equals 0 for all polynomials in this family f. So increasing the set of polynomials means imposing a stronger condition. More polynomials need to vanish on these points, so you get fewer points satisfying this. By the way, feel free to pause and think at any time how any statement is proved, or go back and to the definition and read it again as you wish. Second property, the union of the vanishing set of f and g. Now, f and g are general again, not contained in each other generally. The union of these vanishing sets is the vanishing set of the product family. So this is the set of all products, f times g, with f in f and g in g. The ring is commutative, the ring of polynomials, so it doesn't matter. So why is this true? If you take x here, in the union of these two sets, this means that x is either in one or in the other, or in both. So this implies that either f of x equals 0 for all f in f, or g of x is equal to 0 for all g in g. Yeah, but then if you take the product fg of x, then this will always be 0, because either x is such that f of x will be 0 or g of x will be 0, or both. So yeah, for all f in f and g in g. So this means that x belongs to v of fg. And if x doesn't belong to the union, well, then there will exist some f. So x will not belong to v of f, so it will be not a 0 of some f. And likewise, g of x will be different from 0 for some g in g. Yeah, but then because we are in a polynomial ring that's an integral domain, so then f of x, g of x will not be 0, and it will not belong to this vanishing set. So we have proved that these two sets are equal. More easily, one can prove that the intersection of two vanishing sets is the vanishing set of the union. So this is almost by definition of union and intersection. So x belonging to this intersection means that x is in the vanishing set of f and in the vanishing set of g. So all polynomials in f and in g vanish at x. And this is precisely what it means to be in the vanishing set of the union. Now, the argument that I used, if you back up and listen carefully, the argument I used to prove that the union of vanishing sets is the vanishing set of the product can be extended to 3 vanishing sets. Simply apply this repetitively. And the argument I used to prove point 3, it is valid for any intersection, finite or infinite. So this means that the finite union of algebraic sets is an algebraic set, and arbitrary intersections of algebraic sets are algebraic sets. Together with what we had from the previous slide, that the empty set and the whole affine space are algebraic sets, this should ring a bell if you are into topology, because this says that algebraic sets define closed sets in some topology. We will look into that topology later. Let us now look at 0 log C of ideals. So why would we want to do such a thing? Well, ideals are more well behaved than arbitrary families of functions. Why can we do such a thing? Because of the following proposition. So if you take any family of functions, of polynomials, you look at the ideal generated by this family, then the vanishing set of the ideal is the same as the vanishing set of the family you started with. So from before, we know that f sits inside this ideal, and so by the previous proposition, this will imply that v of j sits inside v of f. Now we need to prove that this inclusion is an equality. Well, j is created. How do we get j? J is created from f by adding elements of the form f plus g with f and g in f, and hf with h in the polynomial ring, and f in f. And such polynomials will vanish at points where polynomials in F vanish. So we do not restrict the vanishing set by adding these functions. And so therefore, in fact, so they don't change V of F. So we have an equality. This is nice because now we know that any algebraic set is the zero locus of a finite set of polynomials. Why is that? So a priori, it's the vanishing set. Pause and think before you listen to the explanation. A priori, it's the vanishing set of some family F of polynomials. Because of the previous proposition, we can say that it's the vanishing set of an ideal. But we've just proved through the Hilbert basis theorem that any ideal is finitely generated because this ring is Noetherian. So then you can take the vanishing set of a set of generators of this ideal. So V of F is V of A1 to AN, where A1 to AN generate the ideal generated by F. And this is, of course, a nice property. And again, there is no canonical way to determine these generators, but you know that they exist. As a corollary of all of what we have said, we can now formulate the properties of the vanishing sets of ideals. So take two ideals, J and J prime. First of all, let's just look at J. The vanishing set of the radical of J is the same as the vanishing set of J. So not only can we look at ideals, but we can look at radical ideals. That is already enough. And this is because, well, so J is contained in the radical of J. So the vanishing set of the radical of J will be contained in the vanishing set of J. But since the radical is just contains functions whose powers lie in J, or some of whose powers lie in J. But if f to the power n of x is equal to 0, that happens if and only if f of x is equal to 0. So it's the same condition on the vanishing set. The union of vanishing sets is the vanishing set of the product. This is exactly the proposition when we looked at the proposition from the previous slide, now with ideals. And the intersection of vanishing sets is the vanishing set of the sum of these two ideals. Now, the proposition says that it's the vanishing set of the union. What you need to check is that the sum of two ideals is the ideal generated by their union. So now we have the basics of algebraic sets, and we can move on and do more complicated stuff with them, more interesting stuff, and that is the topic for the next lecture.